we're going to look at the derivatives of exponential functions. So we're going to look at two formulas here. The first one is the simplest form, which says I want to differentiate e to the x. Now e to the x is actually one of the easiest derivatives ever. It is actually just itself, e to the x. Nothing changes at all. Now most of the time we don't have just e to the x, it would be e to something else, so we'll have e to a function of x, and so we'll have that written as the derivative of e to the u, where u is a function of x. And so in order to differentiate this, we need to apply the chain rule. So I would have e to the exponent times the derivative of the exponent, so times u prime. So here's a basic example to demonstrate this. Let's say I'm starting with y is equal to e to the 2x minus 1. So if I think about this as e to the u, my u is 2x minus 1, and so to differentiate this, I'm going to have y prime is equal to e to the u, so e to the 2x minus 1, times u prime, and u prime is going to be the derivative of the exponent here. Well, the derivative of 2x minus 1 is just 2. So I can write y prime is equal to 2e to the 2x minus 1. So in words, this is just going to be e to the original exponent times the derivative of the exponent, and that is the derivative of this exponential function up here. So let's look at another one. Let's say I'm starting with y is equal to e to the negative 3 over x. Well, before I differentiate, I might want to rewrite this. So this is equivalent to e to the negative 3 x to the negative 1. And now that it's all written as x to an exponent, power rule would work easily when I differentiate the exponent. So y prime, I have e to the u, so e to the negative 3 x to negative 1, times the derivative of the exponent, so that would be times 3x to the negative 2. And of course you could rewrite this so you no longer have negative exponents, but we're going to go ahead and leave it in this form for now. Now as we learn new concepts, of course this continues to mix with old methods or old concepts. So what I want to look at next is applying this to an old concept of finding relative extrema. So when you find relative extrema, first step is you have to find the critical values. Critical values come from where the derivative is either equal to 0 or does not exist. So my first step is I need to find f prime. Well, notice I have two functions being multiplied together, so that's going to require the product rule as well as our new derivative formula for this exponential. So f prime, product rule gives me the first times the derivative of the second. The derivative of e to the x is just e to the x, plus the second, which is e to the x, times the derivative of the first. Well, the derivative of x is just 1, so I can leave it like that. Now there's nowhere this function is going to be undefined, so when I'm finding the critical value, I just need to determine where does f prime equal 0 in this case. Well, notice I can factor out e to the x, which will leave me with x plus 1. E to the x can never equal 0, so I can't solve that half. And so if I just set x plus 1 equal to 0, then my critical value is negative 1. Once you have the critical value, the next step is we have to put that on a number line for the first derivative test. So I'm going to move this up for a moment. So I'm going to draw my number line, put the critical value on there, and then I need to determine what are the signs for f prime around that critical value. So I can plug in some test points. Let's plug in negative 2 on the left, 0 on the right. And I'm plugging that into f prime. So if I take negative 2 and plug that into the factored form, e to the negative 2 is a positive number, negative 2 plus 1 is a negative number, so the overall sign for f prime would be negative. If I take 0 and plug it into the factored form of f prime, well, e to the 0 is positive, 0 plus 1 is positive, so then at 0, f prime is positive. That meant that the original function of f was decreasing, then it went to increasing. This forms a relative min. So the only other thing I need is the y value to have the point for the relative minimum. So going back to the top, I need to determine what is f of negative 1. Well, if I plug it into the original, that gives me negative e to the negative 1, so negative 1 over e. So my conclusion would state, therefore, there is a relative minimum at negative 1 over e by the first derivative test.